2 of this book on the young universe, a recent book. Now, I realize that these books are expensive, so unless you find them in the library or you have a hack version, I hope it's possible, I don't know, then it's not very practical. So I sent this morning, I sent to the organizers a link to the notes of the master course on advanced cosmology that I give every spring semester in Aachen. It does not have as many details as this chapter on the CMB, but it still has lots of details, still a lot more than what we do in the lecture. And this is totally free. I mean, I cannot send you the PDF because I've signed a contract with the editor. For this one, I've signed no contract, so you can have a look at it. It covers a bit of everything. Actually, some topics are stepping on other lecturers, like thermal history of inflation, but you get them as a bonus. But what we are doing here is mainly the chapters on linearized gravity and CMB anisotropy. So feel free to have a look. I think it will be available during the day. Okay, where are we? We stopped yesterday when we were finishing to talk about degrees of freedom and equations. We want to specify degrees of freedom to integrate equations of motion, start from initial conditions, integrate the equations, and get the result. And for this, we started by describing the metric fluctuation phi m psi in the Newtonian gauge, which correspond to two Einstein equations, giving this metric as a function of the total density perturbation and the total shear. Okay, I will let you operate. I do pause on my own timer. Hay que salir de la presentación. Yeah, never behave as you would like to. Escape, maybe, yeah. Good, yes. No problem. Yeah, okay, I go back. Yes, yes. Is it okay? Yeah? Okay, very good. Yes, so we are describing degrees of freedom and matching equations of motion. So we have the two metric fluctuation, and we have two Einstein equations giving the metric fluctuation as a function of the total density perturbation and anisotropic stress. Then if we consider cold dark matter, we introduce two new variables, so the density perturbation and the divergence of the bulk velocity theta, because dark matter is a decoupled fluid, or not a fluid, but a pressureless species, which is like a fluid with pressure 0. So 2 more variables, but also 2 more equations of motion, the continuity equation and the Euler equation, giving respectively the derivative of these 2. So if we would stop there, we would have 4 variables, 4 equations, we would be fine. Oops, sorry. Then we have the baryons. The baryons are a non-relativistic species like cold dark matter, also described by their density and velocity perturbations. And because they are also non-relativistic, they have the same continuity and Euler equation as dark matter. The only difference is that baryons exchange momentum with photons through Thomson scattering. So you have a new term in the Euler equation of baryons, which accounts for Thomson scattering with the photons. And then the tough part is the photon, and this is what we are going to detail now. We say that if we try to describe photon with fluid equations, it doesn't work because we have 1 variable too much compared to the number of equations. And it's in the case for this anisotropic stress, sigma, which is a 3rd variable with no mapping equation when you consider only conservation of energy and momentum. And so we need an equation with a richer structure, which is a Boltzmann equation, which says that along any geodesic, the total derivative of the photon phase-space distribution is given not by 0, because the photons exchange momentum with the baryons, but with a Thomson scattering term. So we have 2 Thomson scattering terms. Actually, they are opposite to each other, because this term accounts for the transfer of momentum from baryon to photon, this one from photon to baryon, and they are the same up to a minus sign. And here we don't have time to deal with neutrinos, but neutrinos would be described by the same equation as photons, except that this term would vanish. This is a typo that I will correct. For neutrinos, we would put a 0 here because we are interested in time, in which neutrinos are decoupled and not exchanging momentum or energy with anybody else. Now we want to understand how to write this phase-space distribution of the photon and the Boltzmann equation, which gives its evolution. So the phase-space distribution of the photon is a function of time, of space, and of momentum. The momentum is a 3-vector that we divide into a modulus, p, and a direction of propagation, hat n, where the hat means it's a unit vector. So we have here 7 degrees of freedom in the argument, and we go down to 6 by saying that we know that the photons have a black-body shape because they have been in thermal equilibrium in the early universe, so they acquired a Bose-Einstein distribution, in which case we know how F depends on momentum through the exponential of P over T here. So we have saved one of the arguments. A big question, very interesting question, is, okay, the photons have a black-body spectrum initially because in the early universe they are in equilibrium. But when they decouple, will they preserve the black-body shape? And that's not a trivial question, because the photons experience different kinds of reactions, of interactions with other particles, described at the end by Thomson scattering, but before there are other reactions that are important, double compton scattering, Bremsstrahlung. And then the photons also interact gravitationally through gravitational forces. And these interactions could push the photons out of this black-body shape, could create distortions to the black-body shape when thermal equilibrium stops to be efficient. That's around the time of decoupling. And the answer is that the gravitational interaction will always preserve the black-body shape. I'm going to show you why. The other interactions, the Compton scattering, etc., they could produce small distortions when photons decouple. But these are very small effects that we would study in a specialized course on CMB spectral distortions. These effects are so small that in an introduction to CMB physics focused on CMB anisotropies, we can pretend that the black-body shape is exactly preserved by these reactions. Okay, so in order to understand, for instance, why the gravitational interaction of the photon preserve the black-body spectrum, we can think about the equation that governs the evolution of the momentum p of a single photon. And it's a geodesic equation. Let's assume that our photons, between two Thomson scattering, our photons travel along a geodesic, their momentum will evolve. We write the geodesic equation to understand how, and it looks like this. It's a logarithmic derivative of AP with respect to time equals some metric fluctuations. Okay, if we didn't have the metric fluctuations, it would tell us that P goes like 1 over A. This is the usual effect of photon redshift, already mentioned by Ruggiero. When the universe expands, the wavelengths of the photons are stretched, so they lose energy. According to the law, P goes like 1 over A. So this is the effect of redshift. But the photons travel in gravitational potential wells. And this is why they will be blue shifted or red shifted, depending on the sign of these effects, which are useful to describe. They are very important for CMB physics, and we will see that they enter in many equations. The first term says that the momentum of an individual photon can evolve if they go through a region in which the metric fluctuation phi has a time derivative. We say that phi is like a local scale factor, so when there is a phi dot or phi prime different from 0, it means locally the expansion is a bit larger, a bit quicker, or a bit slower than the average. And since the expansion acts on the wavelengths of the photons, this local effect will locally stretch or squeeze the wavelengths of the photon and thus redshift them. And this is called the dilation effect. The second effect is the projection of the gradient of the gravitational potential psi along the direction of propagation n. And it's just the usual gravitational Doppler effect that says that if photons are falling in a gravitational potential well, they gain energy. If they need to go out of a potential well, they lose energy, and so they are respectively blue shifted and red shifted, which affects the momentum P. So these are local modulation to the photon momentum. Will this effect produce distortions with respect to the black body spectrum? No. Why? Because this is a logarithmic derivative, dP over P. So it tells you that when photons travel in these metric fluctuations, they all experience collectively the same relative shift of momentum. And this will not change the black body shape. To change it, we will need another P factor on the right. So gravitational interaction preserves the black body shape, but because they are going to produce, for all photons traveling a given geodesic, they are going to produce the same redshifting or the same blue shifting, they will affect, this effect will affect the temperature of photons. And usually when we write a black body distribution, the factor here, the temperature, is allowed to depend on time. The temperature can change. On space, the temperature can be different in different places, but not on direction. What is this? A temperature depending on direction. That's unusual. We are not considering this normally. And indeed, as long as the photons are tightly coupled in the early universe, the dependence on their direction does not exist. But when they decouple, they keep a black body shape, meaning they still obey to this function. There is still a temperature here. It's not anymore a thermodynamical temperature because they leave thermal equilibrium. It's just a parameter in the phase space distribution. And there is no reason that this temperature remains independent of direction, because suppose you are here and you look in different directions you look in different directions n, and you see photons coming from different directions in the early universe. These photons have been traveling along different geodesic and across different overdensities, underdensities with different values of these terms. So they have been redshifted and blue shifted differently, and you measure for them always a black body spectrum, but maybe with a slightly different temperature, which is why this temperature becomes dependent on direction. And this variable, T of eta xn, will be the central, the most important degree of freedom that we need to understand and to integrate over time to understand CMB physics. It's the temperature in a given point at a given time observed in a given direction. And we are going to expand it, as any other quantities in linear perturbation theory, into a background and a perturbation. And we say that T is a background temperature, depending on time, times 1 plus a relative perturbation, theta. So theta is a delta T over T, the relative perturbation of photon temperature that depends on time, position, and direction. And from now on, the theta will be the main function that we want to understand. So, yes?
The black body, why the temperature description doesn't work in the...
So, what happens when photons decouple at redshift of 1000? If they decouple, it means by definition they leave any kind of thermal equilibrium. They are on their own. If a species is not in thermal equilibrium, it does not have a temperature in the thermodynamical sense, because it's not exchanging momentum with other quantities. The definition of temperature is a parameter that describes how a bath of particles in thermal equilibrium exchange momentum. Now that they are, yeah. So in the early universe, they were in equilibrium. So they acquired the black body distribution with a given temperature. When they decouple, this shape cannot change because the interactions that they experience cannot make it change. That's what we say. So it keeps the same shape. So we will keep the same parametrization. We will still call this a temperature just because it's in the denominator of this exponent. But there is no more thermodynamics happening. So it's not anymore a temperature in the thermodynamical sense. It's just formally playing the role of the temperature in a normal Bose-Einstein distribution. So it does not describe anymore a state of thermal equilibrium in which particles are in equilibrium and exchange momentum. It's just a function that describes the phase space distribution of the photons. That's why we call it temperature, but between brackets, because there is no longer thermal equilibrium. It's not even, yeah, it would be their temperature if they were in thermal equilibrium, and we keep calling it temperature, but it's abusing words, because really what we like to call temperature in thermodynamics applies to species that are in equilibrium. But it plays exactly the role of a temperature, and we will keep saying the temperature of the photons. Yeah. Yeah. Yes.
So when you were talking about spectral density,
Yes.
those terms appear because we're like dropping a term in the redshift and the longitude.
No, they appear because if you look at what happens in an individual Thomson scattering or double Compton scattering, etc., these reactions, unlike the gravitational reactions, they don't preserve the black body shape. But if you are well before decoupling, each time that this reaction occurs, it tries to push out of the black body shape. The black body shape comes back because the photon exchange momentum with their environment and go back to the thermal solution. But if you are just at a redshift of, say, 5,000, then the Thomson scattering is taking place. An individual reaction can provoke small distortions, and there are not enough reactions to bring back the black body shape. So you develop tiny distortions that have been understood by people like, of course, Rashid Senayev and his students, and would be the object of another lecture. They are very tiny, we can neglect them here. Yeah. All right. So theta, this is our new important variable. So the fluctuation, the relative fluctuations of this function t at a given time, at a given place, and when you look in a given direction. Okay. Since this function depends on direction, you could try to expand it into multiple, dipole, quadrupole, etc., what is called the Legendre expansion. And you would realize that the first two or even three terms are already familiar to us. The monopole, which is angular average of the theta, gives you what is locally in a given point the relative density fluctuation of the photons, what we call delta gamma before. with a factor 1/4, which is very easy to understand. We have seen in the thermal history of the universe that photons, being relativistic, have a density rho proportional to temperature to the 4. You take the logarithmic derivative of this, you get delta rho over rho equal 4 delta T over T. This means that delta gamma here is 4 times the relative temperature fluctuation. This is why there is a 1 to the 4. So the monopole of theta is a local value of the density fluctuation of the photons. The dipole comes from the fact that the photons have a bulk velocity. So if you are sitting in a given point, because of the bulk velocity of the photon, you perceive a kind of Doppler effect, which has a dipole pattern. So the dipole has to do with the bulk velocity V gamma of the photons that we related in previously to the variable theta gamma. So we could also relate this term to theta gamma. We will see the relation a bit later. So the dipole is a bulk velocity. The next one, I didn't write it here, but the quadrupole of this theta has to do with this anisotropic stress, sigma gamma, that we describe in the energy momentum tensor. The higher multiples can be there in principle, but they don't have an easy interpretation. Well, but we understand what they are. They are just fluctuation of the temperature on small angular scales around the observer. Okay, now we say that the Boltzmann equation has a form like this: total derivative of f along each geodesic equals some Thomson scattering term. Now, I'm not going to lie to you and say it's very easy to show that, because it's several pages of calculation, but you can start from this equation. You replace f by this phase space distribution, and then you replace t by this expansion into perturbations. You compute your Thomson scattering term, and at the end of the day, this Boltzmann equation gives you an equation of motion for theta. And this equation, which plays a very, very big role in CMB physics, is written here. It's a first-order differential equation, because the Boltzmann equation is always third order, and it has several terms that we will describe. Suppose I neglect these ones and these ones. I have just theta prime plus direction of propagation times gradient of theta. This is a traditional equation of propagation. It looks a bit like the square root of a wave equation. But if you try to, for instance, derive the propagation of pressure waves in the air, you will find the same equation. This is equal to 0. It's a propagation equation. So the propagation of sound always obeys to an equation like this, if there is no viscosity, no dissipation, etc. Then here on the right, we have the Thomson scattering term, which accounts for the scattering of photons with baryons, and I'm going to explain its shape. In between, we have metric fluctuation, and the terms here look exactly as before for the geodesic of individual photons. We said individual photons are redshifted or blue shifted by dilation or gravitational Doppler effects. If it happens for individual photon, it should happen also collectively. And collectively means that the shift of all the momenta of photons going into a given direction is equivalent to a shift in their temperature. So we are not surprised to find this dilation and gravitational Doppler term also in the linearized Boltzmann equation. Now, the Thomson scattering term is the Thomson scattering rate times the difference between the bulk velocity of photons and baryons projected along the direction of propagation. Sorry. Not yet fully used to this thing. It's a pity because I love it, actually. Okay. Plus these higher multiples that I did not write explicitly, but theta 2, theta 3, theta 4, etc. What does this term mean? We can think, what does it mean in general in a fluid that interactions are important? This is an interaction term. If gamma is very big, it means we have strong interactions in the fluid. When you have strong interactions in the fluid, you isotropize everything. The role of interaction in a fluid is to isotropize, to make, for instance, the pressure independent of the direction. this is what happens here. Suppose you would work in the reference frame of the baryons, meaning you do a change of coordinate, you go to a frame where the bulk velocity of the baryons is 0. You are left with the velocity and the higher multiples. If gamma is large, this is a Boltzmann equation, so it tells you that if gamma is large, the evolution of the variable will be such that it tries to have 0 in the parentheses. It's always like this with a Boltzmann equation. Quick way to say it is if this goes to infinity, this must go to 0. So the system tracks an equilibrium state where the velocity and the higher multiples are 0, and you are left only with a monopole. It means the Thomson scattering tries to make everything isotropic with no dipole, quadrupole, and so forth. But if I am not in the race frame of the baryons, then there is a shift. The bulk velocity of the baryon appears, and what Thomson scattering says is it wants to have V gamma equal VB, so it wants to align the bulk velocity of the photon and the baryon. They will move together because they are strongly coupled, and higher multiples disappear because of this isotropization effect. So this is what Thomson scattering wants, and this is why the equation has this structure. So at the end, this equation is super intuitive. Okay, what is next? Okay, yes. No, they are all important. They are all. It depends when. So in the early universe, the higher the multiple, the smaller they are. But then once the photon decouple, all the multiples are important, and this is why in a CMB map you see multiples up to L of 3000 or more. In the early universe, they are all 0. Then when decoupling takes place, these higher multiples get all populated, and you should never neglect them. Okay. Yes. So this equation has only one inconvenience. It's an equation of time in which the argument of the function are time, space, and two angles which are hidden in the direction vector. And usually we don't like too much to solve equation with too many arguments. So what we are going to do now is to expand the terms into Legendre multiple and replace the dependence on direction by a dependence on the multiple number L. So we do Legendre expansion in which theta, which was a function of direction, becomes a function of, a set of multiples theta L. And at the same time, we do a Fourier transformation. And after these two transformations, the Boltzmann equation transform into what is called the famous Boltzmann hierarchy, meaning a coupled set of differential equations for all the multiples theta L. So for the first multiple, the equation for theta 0 prime, the monopole, is in fact an equation for the evolution of the density fluctuation. For the first multiple, theta 1 is related to the bulk velocity of the photon, so we have an equation for small theta gamma. And then all the other multiples are accounted by this line, which is for any L bigger than 2. We see here the same source terms as in the previous equation. In the previous equation, the Boltzmann equation was sourced by metric fluctuations that we find here, dilation effect, gravitational Doppler shift, and by the Thomson scattering effect that we find here. Tau prime is the derivative of the optical depth. We said that tau prime is actually the Thomson scattering rate. And we recognize here a term which says that it wants to align the bulk velocity of photons and baryons. When the interaction rate is very big, this will go to 0. And another term that tries to isotropize the fluid and make all the higher multiples vanish. And this equation has an interesting structure. It shows that a given theta L is coupled to its nearest neighbor, theta L minus 1, theta L plus 1. So if you inject power in one theta L, it will propagate to the other L's. And this equation, which is very famous, is still exact if you consider it up to L is equal to infinity. If you don't want to do this, you can truncate it in some way. And it's the equation which is at the core of Einstein-Boltzmann solvers. So what codes like CMB fast, COMB, or class are trying to do is to integrate this equation in combination with the equation we have seen before, which are the linearized Einstein equation and the equation of motion of baryons, cold dark matter, neutrinos, and possibly new species in an extended cosmology. It was nice to give this equation because it's so famous, but we are actually not going to use it in the rest of the course because it's not very practical, it's not very pedagogical. You don't really, when you look at this, you don't really feel what's going on. So to feel better what's going on, we will use a trick and we will go to another way of presenting this problem. You will see this soon. Before doing this, a bit like Ruggiero, I would be blocked if I wouldn't do a bit of blah blah on the stochastic theory of cosmological perturbations. Why is there statistics? Why are there random numbers? What are the initial conditions? So I need to go through a few slides to explain this. There will be a little bit of overlap with Ruggiero, but said a little bit differently, and a bit of overlap is always welcome. And this is also stepping a bit on what Mehrdad will treat, but not too much. Okay, so we need initial conditions for our perturbations. The study of initial conditions in cosmology is very cute. It's very nice to understand how it works. I have to go fast, so I will tell you just the following. You will see in the course on inflation that in a canonical single field model of inflation, where a nice scalar field is rolling down slowly towards the minimum of its potential, there are quantum fluctuations. These quantum fluctuations will be the initial condition for the fluctuations of all the matter fields in the universe. And when you study this problem in details, which you will do next week, you realize 4 big points, A, B, C, D. A is the fact that after inflation, you seed the universe with stochastic fluctuations. Stochastic, why? Because they have a quantum origin, and for some subtle reason, after inflation, you can forget that they are of quantum nature, but they are at least still stochastic, so random variables. And these stochastic perturbations mean that each Fourier mode, the perturbation for a given Fourier mode are independent of the perturbation for other Fourier modes and described by stochastic numbers. So we have stochastic perturbations with independent Fourier modes. B, if they are stochastic, they must have a distribution of probability. It could be anything. Well, in canonical single field inflation, it's not anything. It's Gaussian probability distribution. And you will understand that it has to do with the fact that the fundamental state of a harmonic oscillator has a Gaussian wave function. Yeah. But if it's really on inflation, I will leave it for next week. But please ask. Yeah.
No. This Gaussian.
Yes.
Is it related to Gaussian anisotropic for the CMB?
At the end, yes. If the CMB, fundamentally, if the CMB has Gaussian statistics, it's because the wave function of a quantum harmonic oscillator has a Gaussian wave function. Yeah, absolutely. Then if inflation would predict some non-Gaussian statistics, it could Gaussianize to some extent through the central limit theorem, but fundamentally we don't need this. The answer is yes. Yes, the CMB is Gaussian because the quantum fluctuations during inflation are already Gaussian. Yeah. Okay, so we have these Gaussian statistics, and it tells us that any perturbation can be entirely described by its variance. When you have Gaussian statistics, the variance is everything you need to know, or the root mean square, which is the square root of the variance. However, this variance is still allowed to depend on which scale you are looking at. So the important quantity is the variance as a function of the wave number or the wavelength, and this is what we call the power spectrum. Inflation can be used to show that for each Fourier mode, all the degrees of freedom, these 5 psi, delta c, delta b, theta b, they are all related to each other, meaning they are all fully correlated. This is true in canonical single field inflation, and this is true on super Hubble scales. I'm talking here about super Hubble scales because I'm interested in initial conditions. And this statement is what people call assuming adiabatic initial conditions, but it's not just an assumption, it's something you can prove out of the study of inflation. And it has to do with the fact that all the perturbations in the universe are then assumed to come from a single seed, which has the perturbation of the inflaton field, in such a way that when you describe large scales, super Hubble modes, you can do as if the perturbation of any quantity A, which should be a function of time and space, is given by the background solution that you get in homogeneous cosmology, which is an A bar depending only on time. But in the argument, you put a time-shifting function, meaning that in different regions of the universe, the evolution is fundamentally the same, but with an initial time shift. And this initial time shift has to do with the perturbation of the inflaton field that you will study next week. And it's a very powerful thing, because it means that your perturbation, which would be arbitrary if you didn't have a prescription, becomes a modulation of a function of time only. You can do a Taylor expansion because you are in perturbation theory, and you can expand this into background plus first order Taylor expansion, derivative of the background times this time shifting function, which has to do again with the perturbation of the inflaton initially. And you get a very, very powerful prediction that all the fluctuation of any fluctuation in the universe, delta A, is equal to A bar prime times this time shifting function. This little relation here is amazingly beautiful and powerful. It is really at a deep level what you should call the adiabatic initial conditions. In a book you see many definitions of what adiabatic initial conditions mean, but the fundamental one is this: delta A equal A bar prime delta eta. Once you start from this, you play with the equations of motion, you plug these ansatz in the equation we have already seen, and you can show that for a given Fourier mode, all the fluctuations are related to each other. Delta of photon equal delta of neutrino equal 4/3 delta B or 4/3 delta C, where the 4/3 comes from a relation between between relativistic and non-relativistic species. Using the Einstein equation, you find an equality with a metric fluctuation up to a factor -2 that we have seen yesterday in the Einstein equation already when we were looking at the super Hubble limit. And finally, the Einstein equation, they are differential equations, they are dynamical, they can be solved to give a time evolution. And when you have this prescription, you can integrate the Einstein equation, and you find that in the Newtonian gauge, all these guys are constants. And at the end of the day, what it means is that if you start by assuming canonical single field inflation, you find that on super Hubble scales, everything is trivial. All the degrees of freedom are related by coefficients of order 1 that you can predict, and all these functions are constants on super Hubble scales in the Newtonian gauge. I'm summarizing here in 5 minutes something that would require 1 hour, but if you look in my lecture notes that I advertised at the beginning, you have probably 5 pages on this, and you can get more into the detail. Plus the fact that the next lecturers will probably come back on this. So now we have perturbations that are stochastic Gaussian, fully correlated, and this means that we don't need to know the power spectrum of each variable independently. We need one power spectrum. We know one power spectrum, we know the power spectrum of everybody else. And so we could define, now we have to make a choice. We have to take a convention. Are we going to always refer to the primordial spectrum of photons, of neutrinos, of baryons, of phi, of psi? We can choose, it's totally arbitrary. The choice that people do usually is to use neither of these. I'm trapped now in this Ah, yes. No, that was not the right one. Joder, ¿qué podemos hacer? Volver a cargar. Claro. This is not the right site. Yeah, the problem is that, yeah, but it has to download now. I'm sorry. It's because we did not download them. They are still on the repository. It's not the same as yesterday, you know. Yeah, so we should have explicitly downloaded. Okay, I can go on, and then we will see the equations. Okay, so we have to choose one of the variables that will be a reference. We will specify the power spectrum for this variable, and all the other power spectra can be inferred from this variable. We don't choose phi or psi, or delta gamma, or delta nu. We don't choose the degrees of freedom that we have already seen, because they can still fluctuate at the transition between different epochs. For instance, at the transition between matter and radiation, they can change with time. We choose to calibrate our initial condition with respect to a variable which is truly constant on super Hubble scales. And this variable is called the curvature perturbation. It's just variation in the curvature of three-dimensional spatial hypersurfaces. So we said we work in a flat Friedman-Lemaitre model. Yeah, but it's a background which is flat. When we have perturbations, it's not completely flat. It has small riddles. And so there is a local value of curvature. And this curvature that we will call R is another degree of freedom that we can relate to the metric fluctuation and
the K expanding.
yes.
K is the same K that the power spectrum, or the power spectrum equal I, or K.
You said K expanding. I don't understand what you mean. No.
I want to say the K expanded in the last question.
Yeah.
And I want to know if that K, the letter K,
Yes.
is the same that.
So the K is a wave number, right? So for instance, wavelengths are related to K by lambda equals scale factor times 2 pi over K. Yeah. And so when we look at the equations of motion, we look at them K by K, okay, wave number by wave number, or wave vector by wave vector, actually. And what was your question then? It's probably just because internet was a bit slower for a while that we have all this trouble. Yeah, maybe if there are other questions in the meantime. Yes. Yeah, because if so you can work out different assumptions. You can say, what happens if I don't start from adiabatic initial conditions? You do all the calculation, and you get a prediction for the CMB spectrum, which is very different from the one for adiabatic initial conditions. In the lecture, we will only give the one for adiabatic initial conditions. But if they were non-adiabatic, you could do the same calculation, and you would find a different shape with, at the end, some peaks in your CMB spectrum at a very different scale and with a different shape. And when you confront the CMB spectrum that we will define to data, you find that only the adiabatic initial conditions work. You can even assume a mixture of adiabatic and non-adiabatic, and you see that the non-adiabatic part has to be 0 or negligible. A parameter of non-adiabaticity, there are many actually, because there are many types of non-adiabaticity, especially 4 well-known ones, and you can put constraint on 4 parameters of non-adiabaticity and find that they are all very close to 0. And this is what are called isocurvature modes. So you can look in WMAP papers or Planck papers, the section on isocurvature modes, and you find that they have to be negligible. Okay, I'm very sorry. So where are we now? It's the internet, huh? Yeah. Yeah. Yeah, I should have downloaded it early this morning. I will do this for tomorrow. Yes, other question. At some point, otherwise, we can connect my laptop also, if it's really blocked. Yes, question. Please speak up. Yes. Yeah, it has to do with the way in which you normalize the initial vacuum state of the inflaton. Yeah. But the word adiabatic in adiabatic initial condition doesn't come from there. It comes from fluid dynamics. And okay, I didn't expect to say this, but when you do fluid dynamics, you can consider a multi-fluid, meaning a fluid made of different components. And you can study the properties of the sound speed in this fluid. And the sound speed is said to be adiabatic when the sound speed corresponds to, I defined 2 quantities yesterday, they were called CS and CA, adiabatic sound speed and true sound speed. When the 2 coincide, you say you have an adiabatic fluid. And the 2 would coincide in this situation only if you have these adiabatic initial conditions, and this is where the name adiabatic comes from. It comes from the property of the propagation of sound in a multi-fluid. Oh, wonderful. Yeah. Yeah. Okay, I will repeat the question. I don't have my glasses. Okay.
I want to say if this I is the same I
A.
yeah, A.
So when the question is what was when I explained adiabatic initial condition, there was yeah, we are a bit before. Okay, thank you so much. Sorry for the trouble. The question I just got is what is this A? It's a generic name for any of our perturbations. You can substitute it with delta gamma, delta B, theta gamma, pi, psi, any of the perturbation. It's valid for any of them. That's why this relation is very powerful. It's because this time shifting function is always the same, whatever is the perturbation A that you consider. Okay, so we are back to business. And I was saying that we are going now in our initial conditions to refer always to the same degree of freedom called the curvature perturbation. And the curvature perturbation is denoted R. In the Newtonian gauge, it's given by the metric fluctuation phi minus the total velocity summed over all the fluids. We are going to define the primordial spectrum as the power spectrum, so the variance for a given wave number, of this curvature perturbation. So the curvature perturbation, like any other perturbation, is a function of time and wave vector, We choose an initial time, which one doesn't matter because R is conserved on super Hubble scales. And for this mode K, we take the variance. And the variance is given by first a Dirac delta function. This comes from the fact that, as we said, after inflation and in linear perturbation theory, different Fourier modes are independent from each other. So this variance or this correlation, there is a prime missing here, sorry. There should be a prime here. K and K prime. If K and K prime are different from each other, the Dirac delta function vanishes and it tells us that different Fourier modes are statistically independent. If K and K prime are the same, then the variance is contained by this function that we call the power spectrum of curvature perturbation. And you will, as Ruggiero already advertised and as you will see in the inflation lecture, the simplest model of inflation predicts that this primordial spectrum of curvature is given by a very simple power law with an amplitude and an exponent ns close to 1. So we know the primordial spectrum of curvature, and using the adiabatic initial condition, this gives us the power spectrum of any other quantities at early times that we will plug in as initial conditions in our equations of motion. So we said that inflation makes 4 predictions, A, B, C, D. D is that this primordial spectrum is a power law and nearly scale invariant. We already had this conversation in the previous lecture. So these are our initial conditions. Now, Ruggiero already talked about transfer functions. They are really crucial when in any problem where you study the evolution of cosmological perturbations. The idea is that then for each Fourier mode K, all perturbations obey to a system of differential equations with adiabatic initial conditions. When you have a big system of equations for all the variables, phi, psi, delta, blah, 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 you have n equations. When you solve them, the solution should depend on n constants of integration. And then it becomes a mess. You have to consider any possible combination of these constants of integration to get a finite solution. But thanks to the adiabatic initial conditions, we know that there is only one relevant constant of integration, which can be chosen to be the initial value of the curvature perturbation for the mode K that we are looking at. So for each mode K, there is a single constant of integration. And it means that for any perturbation A in the set of the variables we described before, phi, psi, the densities of species X, the velocity of species X, the multiple of the photons, we can always write the solution of the equations of motion as solution for A at time eta for the mode K equal a constant of integration, which is his initial curvature perturbation for K, multiplied by something that we call the transfer function. And if you think about it, this transfer function is just a solution of the equations of motion normalized to r equal 1. Another way to see it is that you can move r to the left and say the transfer function is A divided by r, meaning the solution divided by r, which is a solution normalized to initially r equal 1. And this is what the transfer function of perturbation A is. Let's look at the arguments of the transfer function. The transfer function depends on eta and on the wave vector k. And it looks like I did another typo here. It looks like I forgot the arrow of the vector k. No, I didn't forget it. I didn't forget it. Here I really have the wave vector and here's the wave number. Why? Because the equation we use describes perturbation in a statistically isotropic universe with an isotropic background. So the equations of motion do not depend explicitly on direction. And this is why the solution of the equation of motion does not depend explicitly on direction either. Meaning that all Fourier wave vector k with the same wave number k have the same transfer function. So it's not a typo that you don't have an arrow on this k. So because of this, there is never a risk to confuse the actual perturbation, which depends on the vector k, and its transfer function, which depends only on the wave number. And as a consequence, in most books or articles, you will find a lazy notation where we don't use a specific letter for the transfer function. We use the same letter as for the perturbation, but without the vector. And later on, when you will see something with a vector, it will be the perturbation. When you will see something without a vector, it will be a transfer function. In such a relation, you have to keep in mind that our initial condition are stochastic. Inflation says that this initial condition R should be a particular realization of a distribution of probability. So a random number or a stochastic number. And then this distribution of probability is Gaussian with a variance described by the power spectrum. So this quantity is stochastic. It means that the perturbation also is stochastic. But the coefficient between the two is deterministic because it's just the solution of the equations of motion normalized to R equal 1. This you can compute without any probability distribution. So we have a stochastic number times a transfer function equal a new stochastic number. And this leads to a very important concept, which is also at the root of the philosophy of cosmological perturbation, which is the concept of linear transport of probability. Each of our variables have a probability distribution, which, as we said in standard cosmology, is Gaussian. So it means that if I look at the perturbation for a given wave vector k of a given degree of freedom A, it has initially a distribution of probability. Later on, A evolves according to this linear equation. And I can compute the distribution of probability of A at a later time. And I can do it by thinking that A can take various realizations. And once you have chosen a realization, you propagate it from initial time to late time by just multiplying with a transfer function. But this is a linear relation, meaning that if I have a first realization of A and a second realization which is twice bigger, at the end, this will predict that at a later time, the first realization gives the first value of A, the other one gives also a twice bigger value of A. So you have a linear evolution of the classical trajectories, meaning that as a whole, the probability distribution cannot change its shape. This is what is called a linear transport of probability. The only thing that can change is that depending on the fact that the transfer function is bigger than 1 or smaller than 1, the probability is either stretched or squeezed. So the only thing that will change with the evolution of cosmological perturbation is the root mean square, or the variance, of the perturbations. And the transfer function gives the evolution of the root mean square, meaning that the square of the transfer function gives the evolution of the variance. And at some point, you can almost forget this relation. You solve your system of equation for transfer function, and you should realize that what you are solving is the evolution of the root mean square of your Gaussian stochastic fluctuations. This is really the meaning of the transfer functions. If this is not clear, it's probably my fault and you can ask questions, but don't leave the school without understanding this if you want to do ever cosmological perturbation in your research, because this is at the center of the philosophy of linear cosmological perturbation theory. This story of initial condition, transfer function, and linear transport of probability, this is absolutely crucial. You go nowhere if you don't understand this. Questions? Adiabaticity and linearity. Adiabaticity is a reason for which you have a single constant of integration rather than a long sum of constant of integration times its own transfer function plus second constant of integration times its own transfer function. You could have a long list in principle. There is only one because of adiabaticity. But then it's because we have a linear relation, it's because we have linear equations of motion, that we have a linear solution, and that we have this linear transport of probability. Okay. Good. We go on. Yes. Okay. Power spectrum. Now, if you understood the previous slides, this one is trivial. So the fact that we have adiabatic initial conditions and linear transport of probability tell us that for any perturbation A at any time eta, if I look at the correlation between two modes, A of k and A of k prime, meaning I take the variance of A times complex conjugate of A, I need a complex conjugate because I'm working in Fourier space. In Fourier space, the quantities are always complex. So this is how we define the correlation between the mode k of A and k prime of the same variable. So we compute this expectation value over several realizations of our stochastic theory, and we can substitute each of these two with the previous relation. A is equal to transfer functions times r for k. A star is transfer function times r of k prime. So we replace, and we have this correlator. And this correlator is what we define to be the power spectrum of curvature. So in the next line, I just replace this by the modulus square of the transfer function, and this correlator by the power spectrum times the Dirac delta function. Nothing new here. And what appears to be the coefficient in front of the Dirac delta function is then now the power spectrum of the variable A at the time eta. And we have a confirmation of what we expected. When we have to compute the power spectrum of a given variable, we don't need to reinvent the wheel. We can just compute its transfer function. And the power spectrum is given by the square or the modulus square of the transfer function times the primordial curvature spectrum of R. And this is what I meant when I say, if I know the primordial curvature spectrum of curvature, I know all the rest. So this is how you decompose a power spectrum. This was actually already there in the slides of Ruggiero. He was focusing on the growth of cold dark matter fluctuation in the lambda CDM model. In this case, there is one simplification. It's the fact that this transfer function can be separated into a time function, time a function of k. But in general, and in particular in CMB physics, this is no longer the case. You cannot separate this function into functions. Okay, so this is some general concept, general formalism, and I think now it's time to apply it concretely to our CMB problem. And we are now heading towards the definition of the crucial quantity of the lecture, which is a spectrum of temperature anisotropies. All right, so we see photons that have decoupled when the universe became transparent. They come from different geodesic. We see them when we look at different directions. We can do an approximation that will help us to understand what's going on, but this approximation is actually not made in the calculations that I will present. We say that most of the photons come from recombination. So I'm going to neglect reionization and do as if they would all come from recombination for the moment. And I will do as this visibility function defined yesterday was very peaked. If it's very peaked, then really all the photons had their last interaction on a sphere. In reality, it's not so peaked, so the sphere has a thickness. We will come back to this in due time. All right, so these photons come from the sphere, and they carry information, at least information about what was the local value of the temperature in different points of the sphere. And this is why, at the end, we expect to have a map of temperature anisotropies with different values in different directions. So we map this. We are COBE, we are WMAP, we are Planck. We map these temperature fluctuations as a function of the direction of observation. And if we try to relate this to our variable theta, this is an observation that we do today. So it's our temperature fluctuation theta, the one of the previous slides, today, at our location, the one of the instrument or of the Earth or the Lagrange 2-point or whatever, that I put the origin there for simplicity, but there is nothing deep about this. And I put a minus n. Why? Because in our definition of theta, this was a direction of propagation. If I look at photons in the direction n, it means I look at photons propagating in the direction minus n, which gives a minus. Okay. This is my map. What do I do with my map? I expand it into spherical harmonics, and the information is now in the multipoles ALM. And it would be nice to invert this relation. Here we have theta as a function of the ALM. Suppose I want ALM as a function of theta. You know, when you study spherical harmonics, there are plenty of relations of orthogonality which are designed precisely in such a way that we can invert the relation. So we can invert it, and we can express ALM as a function of theta, and moreover, we can expand this theta in Fourier space and in Legendre multiples, meaning that at the end, after doing just some basic math, which is detailed in my notes, we can express ALM as a function of the Fourier and Legendre transform of this theta. And let's look at it. ALM is now related to the multiple of the photon fluctuation, theta L, today for the mode k, with an integral over k, over the wave vector k, and a kernel given here by the spherical harmonic in the direction of my vector k. This spherical harmonic carries two indices which match with the two indices of ALM. Okay, if I would go fast, this is typically the kind of calculation I would like to do on the blackboard for you, but if I don't have time to do it at the end, I think you find it in my lecture notes, unless it's in some exercise referring to the lecture notes that I could put also online. All right, so we have ALM as a function of this variable, and now we are curious to compute the correlation between two ALMs. So ALM and AL prime M prime. We have here again a complex conjugate because the ALMs are complex, so it's natural to put a complex conjugate. And then we try to evaluate the expectation value of this product. So to do this, you need to replace ALM by this expression, AL prime M prime by the same expression with a K prime, L prime and M prime, okay? And the correlator now will act on the correlator for theta L. So we will have the power spectrum of theta L. What is the power spectrum of theta L? According to the previous slide, it's the square of the transfer function for theta L times the power spectrum, PR, times the Dirac delta function of K minus K prime, and you use this Dirac delta function to get rid of the second integral over D3K prime. And after getting rid of it and arranging all the factors, you still get an integral of YLM K, Y, L prime, M prime, K prime, a K again, over all directions. And with the orthogonality relation of spherical harmonics, this gives you some Kronecker symbol of delta LL prime, delta MM prime. And at the end of the day, you realize that if L is not equal to L prime or M equal not M prime, this correlator vanishes, so each ALM is statistically independent. If they are equal to each other, this correlator gives you the variance of the ALM. The variance of the ALM is given by an integral over all Fourier mode of the square of the photon transfer functions times the primordial spectrum. And it is this quantity here between the brackets that we will call the temperature power spectrum. Note that it depends only on L. There is no reference to M here. This is again because we live in an isotropic universe. L, the multiple L refers to angular scales, but the multiple number M to different configurations, so different orientations of your multiple. And the correlator here cannot depend on M because of isotropy, for the same reason as the power spectrum depends on the wave number K, but not on the wave vector K arrow. This temperature power spectrum plays a central role in CMB physics. After all, for a simple reason. It's because it is the quantity that we can easily predict with the theory and easily measure with observations. So it makes a connection between theory and observations. From the point of view of the theory, it's given by this relation. And in a given cosmological model, you can compute it. You split the problem in two. First, you study inflation, gives you the primordial spectrum. Then you integrate your equations of motion normalized to R equal 1, gives you the transfer function. You do this convolution, you get your CL, you have a prediction for your cosmology temperature power spectrum. If you change the model of inflation, you change this. if you change omega B, omega CDM, H naught, etc., you change this solution. So it's depending on all cosmological parameters. As an observer, what do? You cannot do this average. This average is an average over all realization of a stochastic theory. So to compute this average, you need to observe many independent universes. Okay, you cannot do this, but you can build what people call an estimator of this average. An estimator is when you try to infer the properties of a dice from a finite number of realizations. And this estimator can be built in a very natural way by noticing that the correlator is independent of M. So if I measure just one ALM and I take its modulus square, I have an estimate of CL, but a very bad estimate. If I consider two values of M and I take the average between the two, the CL I will get will have a chance to be closer to the true CL. I can do this for all the M's associated to a given M. You know that M can vary between minus L and L. So I do an average. I assume that I have a CMB map. I've measured all the ALMs. I take their modulus squares. I average over all the ALM square with a fixed L, but for all possible values of M. I have 2L plus 1 values of M in this sum. So the average has a 1 over 2L plus 1. And what I get is an estimator of the true CL. And if I have many values of M, my estimator will be close to the true CL. How close? It's a classical calculation that you can do. You can compute the variance between the estimator and the true CL, meaning that you take this equation, CL hat minus CL square, you replace CL hat according to this equation, and you take the correlator, now considering the ALMs as stochastic variables. After expanding, you have a 4-point correlation function with 4 different ALMs. But these ALMs are Gaussian. So what do? You use Wick theorem, the same Wick theorem as in QFT, to express your 4-point correlation function as products of 2-point correlation functions. You compute, see my notes, and you get CL squared times 2 over 2L plus 1, meaning some number which will be small when L is large and big when L is small, because of the L here.
Excuse me, Julien.
Yes.
Why is the estimator of the CL is one fraction 2L plus 1 times the sum?
Okay, this is an average. So I take an average, so I sum over n quantities divided by n. The number of ALM squared over which I can sum is 2L plus 1, because for spherical harmonics, M is defined between minus L and L. So if you count, this gives a 2L plus 1. So I take the sum over these 2L plus 1 numbers, and I divide by 2L plus 1. Yeah. Very good. Now, why is this difference between the true value and the estimator smaller when L is big? Because when L is big, I can estimate CL by averaging over many realizations. And so I expect my estimator to be close to the true value. If I look at the quadruple, then L equal 2, I have only 3 values. I can only average over 3 values. I get a bad estimate. It's like if you want to understand if a dice is true or is biased, you will understand it better after throwing it 1,000 times than after throwing it 3 times. And this effect is called cosmic variance. It means that the CL that we observe are not meant to be equal to the theoretical CL. They are meant to be close to them, and how close is given by this formula. And you can see it very well, for instance, in the Planck spectrum. In the Planck spectrum, the red is the best fit. This is CL as a function of L. I will comment on this normalization later on. CL as a function of L. And of course, we are going to explain why there is this very interesting structure of peaks. But if you look at small l's, the measurements are accounted by these black dots. And they are very scattered at small l and not very scattered at large L. This is because this cosmic variance decreases. And so it is normal that the measurements here are always closer to the theoretical prediction than for large angular scales, small multiples L. This is cosmic variance. And okay, this is the crucial role of the temperature power spectrum, which is now what we want to evaluate, because this is what we will be able to predict and compare to observations. And this opens a new part, which is probably the central part of the lecture. Yes, first we have one question. Yes, we will study this. The L's are the multiple number. And what is a multiple? It's a pattern such that between a maximum and an adjacent minimum, there is an angle of pi divided by L. So there is a relation between multiples and angles. We are going to detail this a lot. Yes. Yeah. So for the quadruple, a maximum and a minimum are separated by pi over 2, then pi over 3, pi over 4, etc. And a very large L means very small angular separation between maxima and minimum. Okay, very good. Physics of temperature and isotropies. Don't hesitate to cut me when the 5 minutes are over, because I can stop at any point. Okay, I told you we don't want to bother with the Boltzmann hierarchy because the physics is not so clear when you discuss solution to the Boltzmann hierarchy. So we are going to use a trick. The trick is to consider a formal solution of the Boltzmann equation. Formal solution means you write an integral solution. When you plug this integral solution into your equation, you can see that it solves the equation. But still, you are not completely done, because what you have in the integral are perturbations as a function of time, and you still need to work and integrate the equation of motion to understand what the integrand is. This is always the case with these formal solutions. And in the case of the Boltzmann hierarchy describing the CMB, the formal solution for the perturbation of the photon in Fourier and multiple space was found by Matthias Aldariaga, who is coming next week, and his supervisor when he was a master student in this building, Diego Harari, in 1995. This is a very famous paper. And they found that the formal solution gives the photon transfer function today. This is what we need. This is really what we need to plug in into the CLs. As an integral over all times between the early universe and today. In fact, what matters is that this time is taken just before photon decoupling. You don't need to go before. It's an integral over time. And in the integrand, you have 3 terms. And in the 3 terms, there is always the same structure. There is a function of time. There is a perturbation depending on time and wave number. And there is a spherical Bessel function, JL, with this argument k eta 0 minus eta. So we see it in these 3 terms. And now what is the structure of, this is a mathematical structure of the equation. What is the logic of the equation? The logic of the equation is to say that the transfer function of the photon depends on a list of physical effects. This one, this one, this one. And for each physical effect, the physical effect is relevant at a time described by this kernel, by this function. So the place where this function peaks is the time at which the effect is important. Okay? This effect, so, is important at a time described by the function here. The effect comes from the perturbation A, and A can be one of these variables. So it means that each of these perturbations has a given impact on the photon transfer function. And it projects from the Fourier space to the space of multiples according to this mysterious spherical Bessel function. And we are going to now try to understand this better. So, and then we will go through all these effects, probably not today, but tomorrow. So, very beautiful equation, and it's worth describing it a little bit more into detail, spending time on this. You could put an arrow here or not, because this equation is valid both for a given Fourier mode with an arrow, and then it's a stochastic number, or for a transfer function k without the arrow, and then it's normalized to r equal 1. I didn't write all the arguments here, but the green functions are depending on time, and the red functions are always depending on time and wave number. And if I put a vector k here, I should have a vector k in all these arguments. It means that I'm finding a relation between the actual modes, which are realization of a stochastic theory. If I don't put the arrow on the left, I should not put the arrow in the arguments of these quantities. It means that I have divided my whole equation by the curvature perturbation, and I'm now dealing with transfer functions normalized to r equal 1. Okay, I guess it's 1-2 minutes, or yeah, maybe one more slide. I think one more slide is nice, because you are probably very intrigued. What the hell are these spherical Bessel functions doing here? They play the role of projecting our Fourier modes to multiple space. And this is what we want, because we have defined our perturbation in Fourier space, but now we are trying to compute an observable in multiple space. And this projection, and this will be my last slide today, is accounted for by this spherical Bessel function. Let me remind you the shape of a spherical Bessel function. It's an oscillatory function. It's almost 0 up till a value of the argument equal to the integer here. In my example, it's j10. So until 10, it's 0. Then it has a huge peak at x equal L, in this case 10, and then damped oscillations. Why is this accounting for a projection? You should imagine that you have a Fourier mode around an observer. Fourier mode is a plane wave. A plane wave with maxima, minima, etc. Suppose that you observe the Fourier mode on a sphere. You take a spherical cut of your three-dimensional space. This Fourier mode then will generate anisotropies in the form of rings on the sphere. And now suppose you do a multiple expansion of this pattern. To which multiple will your Fourier mode contribute? And this is the question answered by the spherical Bessel function. And the answer depends on the radius of this sphere. Let's consider this small radius b. In b, we see that maxima are in red and minima in blue. We see that maxima and minima are separated by this angle theta. So we expect that this Fourier mode will mainly excite a multiple such that the difference, the angular separation between a maximum and a minimum, is given by theta. And this is accounted by this equation. Theta corresponds to the multiple pi over L. This is what we just said. But theta is the angle under which I see half of the wavelengths of the Fourier mode, lambda over 2, divided by, in flat space, it would be the radius of the sphere. In cosmology, it's the angular diameter distance. I replace lambda by a times 2 pi over k. That's the definition of wavelengths in cosmology. And the angular diameter distance is actually the scale factor times an integral of dt over a, which is d eta, and this integral is just eta 0 minus eta. I simplify by the scale factor, and this relation gives me L equal k eta 0 minus eta. So I expect that a Fourier mode seen on this sphere will mainly excite a multiple such that the relation between the multiple number and the wave number is L equal k eta 0 minus eta. Fine, because this is what gives the maximum of this Bessel function. The maximum of the Bessel function is when the argument is equal to the index. It's exactly this relation. So we could almost expect a Dirac delta function peaking here. Why do we have these damped oscillations? Because we have to consider also the harmonics. And this is what these other spheres are expressing. For instance, I have a contribution to the same theta of this mode, which is located further away from me, with a pattern minimum, maximum, minimum, maximum, minimum, maximum. So it also contributes to creating a maximum and a minimum with a separation angle of theta. So all these are the harmonics, and the harmonics are the reason for which we have secondary peaks that are smaller and smaller. And so to conclude, if I come back to my previous relation, before entering into the physical description of this, we understand that we have spherical Bessel functions here, because here we have Fourier mode, and we need to multiply the Fourier mode by the spherical Bessel function to know how much a given Fourier mode k contributes to a given multiple L. And tomorrow we will go on, and we will try to interpret the other terms, the green and red terms, and this will give us the physical mechanism at play in CMB physics. Thank you. Yes. Sorry? The power spectrum is defined at any time. You can evaluate it at any time. So when people talk about the matter power spectrum, they mean the one at the time of the observation, for instance, which is at a small redshift. Ah, the primordial one. Very good. So the primordial one, you don't need to specify, because the curvature perturbation has this wonderful property that after inflation, or even during inflation, it is conserved on any super-Hubble scales. When you define your initial conditions, it's always at a time when they were on super-Hubble scales. And then R, for a given Fourier mode k, R does not depend on time anymore. So it could be defined at any time. In my slides, I had an eta initial, but you just need to be sure that this eta initial is sufficiently small such that the mode you are looking at is on super-Hubble scales, and then the precise value of eta initial no longer matters. Strictly speaking, it could be even during the end of inflation, provided your mode is already on super-Hubble scales. Yeah, usually people will say at the beginning of radiation domination on super-Hubble scales, but if you are playing with a canonical model of single field inflation, then R is also conserved on super-Hubble scales during inflation, and you could even define it there. Yeah. Yeah. Yeah.
When you say observation, Planck, for example,
Yeah.
they have a lot of frequencies. It's a spectrum of electromagnetic waves.
Mm-hmm.
How do you convert to the CL?
Well, first you need to convert to temperature. So I will have a section on observation in the fourth lecture, but I will not go too much into these details because this is really remaining a theory lecture. However, to answer you, so you have an observation of the photon anisotropies at each frequency, and you do a spectral analysis to separate your different maps into a map of a black body signal and maps of non-black body signals, which are foregrounds. And at the end of the day, so you start with 14 maps at different frequencies, you combine them, you filter them, and you get one map for temperature. And once you have the map of temperature, you can expand it in spherical harmonics and do this. Now, what I describe is a bit academic. It's not, in fact, what we did inside Planck and what people do in other experiments. They keep different maps at different frequencies. They just change the units such that at each frequency you rescale your observation such that it accounts for the map of temperature anisotropies inferred from a single frequency. And then the data is like a sum of maps at different frequencies called different channels. And this is, at the end, what you fit is you fit the theory to these different maps. Yeah, a template. Yeah. No, because you don't play anymore with, so you correct for the frequency dependence initially, and you convert each of your observation at different frequency into a temperature map. And then you have a sum of temperature maps that you expand into ALMs, but you have ALMs for each channel, and you fit the data to the ALM for each channel. Yeah. No, but no. In COBE, there were two different instruments. One measuring only the black body without angular information, and one measuring only the angular information at different frequency. So COBE-FIRAS was not used to get the CL. And with Planck, it's the same. You measure your fluctuation in different frequencies. You remove, by doing filtering, anybody which doesn't look like a black body. And you end up with estimators of the temperature map that you can expand in multiples, and then you fit the CLs. Yeah. Yeah.
Yes, in the last slide, the vessel function, the image.
Yes?
Yes. What does it mean, the first image? The second,
Okay, this image means, okay, assume that I have a Fourier mode propagating everywhere in my universe, and I'm the observer. And this Fourier mode has, at a given time, just this plane wave pattern with maxima and minima. Now, suppose that I have a way to measure this Fourier mode only on a sphere. At the end, this is what we will do when we measure the CMB. The CMB gets a contribution from Fourier modes, but we only see them on one sphere, which is a last scattering surface. And if I take the cut, the spherical cut, this Fourier mode will imprint rings on my sphere. And these rings will contribute to some multiples more than some others. And the Bessel function tells you to which multiple a given Fourier mode contributes. And the contribution is maximum when you are in the ideal case where an adjacent maximum and minimum are seen under an angular separation pi over L. And this corresponds to the first peak, the other one to the harmonics. You know.